the real result for sure. You can using the quantified approach, but don't forget that is the just one topic. How about the safety analysis? Finally, you still need to draw the isomorphic line. Okay, for safety analysis. So that will not be using this in the first time. Okay. Okay, let's go to the safety analysis. Okay, the first one that I said, look at this. This is objective function, right? I'm saying that for safety analysis, we're gonna allow it to change just only one parameter. And for the objective function, only one parameter that it can change is about the coefficient instead of x. Unit profit or unit cost. So in this case, safety analysis, we're gonna find what we call range of optimality. Range of optimality. This is the range of changing the coefficient in front of x1, x2 in the objective function. And this is about range, right? Range, so you need to have like the limit, lower limit and upper limits. And since you calculate by hand, so we can find just the range for CX1 and CX2. So this is what we try to find, range of optimality. Range of changing the coefficient in the objective function, right? CX1, CX2. We try to find lower limit and upper limit. Okay. And if I go to this one, again, this is a solution for the previous example, Stratton Company. Remember, we have three constraints, right? Extrusions, packaging, additive mix. We find out that, okay, price C is optimal solution, X1 to X26. And now, we try to find the range of changing this coefficient. Another way is, if this one is not 34, what kind of the range that we allow to stay within the lower and upper limit, and for 40 as well. We're going to find this range. This range for what? The range of changing this coefficient in order to have the same optimal solution at price C. We try to find the range of changing coefficient in front of x1 and x2 that can still make that the problem have optimal solution at price C or x1 to 3, x2 to 6. And one thing that you can notice here, if I try to find a range of coefficient here, 34 or 40, actually it's about changing the slope of isomorphic line, right? Changing the coefficient in front of x1 and x2 in the objective function, this means we change the slope of isomorphic line, right? So on the other hand, we try to find the range of the slope of isomorphic line actually. And now I want you to pay attention here because I have the very low skill of PowerPoint making. So I need you to imagine by using my explanation in the air. We have no graphic anymore. Okay, look at this. Original problem. Original problem. The dashed line is isomorphic line, right? Maximization you project in this direction. And finally, you have price C is optimal solution. Now, if I say that, okay, if the slope of this isomorphic line, slope of this line change a little bit, let's say that it change clockwise just a little bit, and not equal to the slope of packaging yet, just like this. When you do the third step of graphical method, project to find the optimal solution, you can find that price C still be your optimal solution, right? And now, if the slope is changed to change clockwise until it equal to the slope of packaging, what happens? When you project to find the optimal solution, the isomorphic line is going to perfect match with the packaging constraint. And price C still be one of your optimal solution point. But if you change the slope of isomorphic line more than the slope of packaging constraint, let's say something like this, and when you project to find the optimal solution, you can see that price C is not your optimal solution anymore. Optimal solution is going to occur at ID. So now, what does it mean? It means that if you want the optimal solution still at price C, when you change the slope of isomorphic line clockwise, the slope needs to be at least not more than the slope of packaging constraint. On the other hand, if I check the slope counterclockwise a little bit, and the slope is not equal to the extrusion yet, just right here. When you project to find the optimal solution on the third step of vertical method, point C still will be your optimal solution. If you change counterclockwise until the slope equal to the extrusion constraint, and when you try to project, it's gonna perfect match, right? With extrusion, and point C is one of your optimal solution point. But if your slope is changed counterclockwise more than the slope of extrusion, just like this, when you project, it's not point C to be your optimal solution, but it's point B instead to be your optimal solution. So in this case, it means that if you want the optimal solution still occur at point C or x1, 3, x2, 6, the slope of isophyll line need to change within the slope of packaging and extrusion, right? Just like the way that you look at point C to be the center point of changing the slope, that your slope of isophyll line needs to lie between packaging and extrusion in order to getting point C to be optimal solution point. And do you still the way that we finding the slope? Remember? This one I use x2, this one use x1, or we said x2 equal to ax1 plus b. This is slope, remember? The open. So, right? So we have, for example, this one. Okay, 2x1. So that's why we have 2x1 plus 2x2 less or equal to 18. If we want to find this slope, it's similar that we have the 2x1 plus 2x2 equal to 18. So then you have 2x2 equal to minus 2x1 plus 18. x2 is equal to, right? So this is the slope. Right? So that's why the slope of packaging is minus 1. Remember the way that we finding the slope. Okay? So I'll just show you about the why the slope of packaging is minus 1. And how about this slope extrusion is minus 2 over 3. This come forward, we change 4x1 to this side, right? And then divided by 6, right? So we have the slope is minus 2 over 3. Okay? So this is the old map. Okay, just in case you cannot remember. But how about isophyll line? Look at this. The isophyll line you have the equation Z or total profit equal to Cx1 plus x1 minus Cx2 plus x2. So I'm going to have Cx2 minus multiplied with x2 equal to minus Cx1 x1 plus z, right? So then x2 equal to minus Cx1 over Cx2, remember? x1 plus c over Cx2, right? So this is the slope, okay? This is general form of isophyll line. So back to the example. Okay, this is general form of the slope for isophyll line. So if I back to this one, what happened? We know that if you want the optimal solution occur at point C or x1, 3, x2, 6, the slope of isophyll line you need to stay between the slope of packaging and slope of extrusion. Slope of packaging constraint is minus 1. Slope of extrusion is minus 2 or 3. Can you tell me that minus 1 and minus 2 or 3, which one is the greater value? Minus 1 and minus 2 or 3, which one is the greater value?
Minus 1.
Minus 1. Come on. Minus 1 and minus 2 or 3, which one is the greater value? Minus 1 and minus 2, which one is the greater value? Minus 1, right? So in this case, minus 1 and minus 2 or 3, which one is greater one? Minus 2 or 3, right? So, if we want to have point C still be your optimal solution, look at this slope of additive function or slope of isomorphic line. You see, minus 6, 1 over 6, 2. This is the one that I just showed you, okay? This is the one that I just showed you, right? These two lines will be the slope of packaging and extrusion. So that's why minus 1 needs to be on the left hand side because it's the lower one. Greater equal to minus 1 and less than equal to minus 2 or 3, okay? Okay, because this one is greater value than this one. Okay, don't be confused, minus 2 or 3 on this one and minus 1 on this one, you're gonna wrong. Okay. Right. And what happened? If you're setting up this, you're on the right hand. Okay, this is the range of automotive, but remember that safety analysis, we allow just changing only one parameter at a time. So that's why we need to split into two cases. The first case and the second case. The first case is, we assume that coefficient in front of x1 is still the same as 34. It doesn't change. We try to find the range of CX2. Another case is that we assume the coefficient in front of x2 is equal to 40, not change. And we try to find the range of CX1. Okay. And during the analysis, this is the old knowledge. Mathematics. Let's say, for example, if you're using CX1 to be the same as 34, you're going to have minus 1 less than or equal to minus 34 over CX2 less than or equal to minus 2 over 3. Which means you can split into two minus 1 less than or equal to minus 34 over CX2, minus 34 over CX2 less than or equal to minus 2 over 3. Right? And we're going to forget some requirement that if you still using the math, you say that, okay, we can use CX2 multiply for all, and CX2 needs not to be the 0, yes, so it's not occur for sure. So that's why we use CX2 multiply for all. We're going to have minus CX2 less than or equal to minus 34. This one, you use CX2 multiply for all, and then using 3, right, to multiply this one, and 2 divided by this one, you can have minus 51 less than or equal to minus CX2. And then you're using minus 1 multiplied for all. And 6 now going to change. Finally, we have CX2 greater or equal to 34, CX2 less than or equal to 51, and then you intersect together. You're going to have the range of CX2 in 34 and 51 as an upper limit. So what does it mean here? It means that if the unit profit of X1, type 1 type, or CX1 equal to 34, nothing change, doesn't change. And the unit profit of type 2 pi or coefficient of X2 change from 40 to any value lying between 34 to 51. You're going to have the optimal solution at place C, X1, 3, X2, 6 for sure. No need to recalculate. But if coefficient in front of X1 is 34, but coefficient in front of X2 is changed from 40 to other value that out of this range, for example, 55, optimal solution is going to change. You need to recalculate. You cannot tell about the optimal solution anymore. You need to recalculate to find a new answer. On this side, we do the same. We try to find the range of CX1 by substitute CX2 to be the same as 40. So you have minus 1 less than or equal to minus 6, 1 over 40, less than or equal to minus 2 over 3. We split into two groups. Minus 1 less than or equal to minus 6, 1 over 40. Then you have 40, split multiply here. You have minus 40 less than or equal to minus 6, 1. Minus 1 multiply for all, change the signal. So we have 6, 1 less than or equal to 40. This one as well, you split multiply here. You have minus 6, 1 less than or equal to minus 80 over 3. And then you use minus 1 multiply for all, change the signal. 6, 1 greater or equal to 80 over 3 or 76.67. Then you intersect these two together, you're going to have this range. So it means that if the coefficient in front of X1 equal to, if the coefficient in front of X2 equal to 40, and doesn't change, the coefficient in front of X1 it change lie between 26.67 to 40, you can know automatically that, okay, the solution, optimal solution X1 to be equal to 6 by C. But if the coefficient in front of X1 is changed out of this range, let's say it's 50, So you cannot tell that optimal solution is x1, 3, x2, 6 anymore. You need to recalculate. Okay. So this is the range of optimality. This is the most difficult one, actually, for the real problem. Because we're dealing with the slope. And one thing that you can see here, that this problem is just 3 constraints. And the constraint is very simple. Actually, if we ask you to find the range of optimality, you can look at the center point to rotate between the of the isopropyl line between these 2 constraints. And you solve for the map as this slide, the previous slide. But sometimes the problem is more complex than this. What happens if you have more than 3 constraints? Some constraint is parallel to x2 axis. Some constraint is parallel to the x1 axis. Some constraint is, have the slope change from plus to minus to plus something. So it's quite difficult, right? And don't think too much for that one. Now I just want you to understand the example only. Okay, if you understand the concept, that's fine. So this is what we call the range of optimality. This is the first one of the safety analysis. So the benefit is that, for example, here, you do analysis. Okay, finally, at optimal solution x1, 3, 2, 6. Let's say that something changed. Unit profit of x2 changed. It changed from 40 to, let's say, 35. If you don't have the knowledge of safety analysis, what happened? You recalculate everything. You change this one to 35, and then you solve for the new problem again. Right? Spend time. But if you have the knowledge of safety analysis, okay, it's changed to 35, right? Let me check with the safety analysis. Let me check with the range of optimality. 35 is still in the range. I don't have to do the new calculation. I can tell that, okay, you still make x1, 3, x2, 6. You still have the maximum profit. Okay? And if you want, if you study more, let's say in the next 2 weeks, on the week that we're using the software program. The software program, we provide everything for you. Right? Just like this. It's going to provide the result for you. All the job that we have to do is look at the result and we can know. Right? What is the answer? Okay. No need to recalculate if you have the knowledge of safety analysis. But if you don't have it, what happens? You need to recalculate again and again, so spend a lot of time. Okay, so this is the first part, range of optimality. The change in the coefficient in the objective function, or the change of the slope of isotropic or isocross line. Okay, and one more question. In this case, besides additive mixed constraint, do we have any non-binding constraint? Besides additive mixed constraint, do we have any non-binding constraint? Yes. And this is x1 and x2 axis. x1 and x2 is non-binding constraint, right? Remember that x1 and x2 will still be our constraint, right? And it's still be the non-binding constraint because it's not provided for C. So, okay, so this is the first set of the slide. We go to the next one. Okay. At the moment ago, we just analyze change in the objective function, change this one. How about do one more example? If I use the old example that we have done last week, the example of the Fair Furniture Company. Remember the company that produced table and chair last week? And this is the solution about the equation. we try to maximize the total profit equal to 7x1 plus 5x2. We have two constraints, right? Currency hour and pending hour. And this is the result. This is the result, remember? Okay, based on the result, what do we have here? If you confused about the previous example, you think that you don't understand much about the safety analysis. Now, this is about the time that I'm going to review for you again. Look at the example. We saw using the graphical method, and we have the optimal solution at point C. The coordination x130, x240. Based on this example, x130, x240, both are not zero value. So we call both basic variable. At point C, optimal solution is occur from constraint 1 and 2 cutting together. So constraint 1 and 2, currently and pending, both are binding constraint. Okay. In this case, we do have non-binding constraint, which is the x1 axis and x2 axis. Okay. If I want to find the slack or surplus, in this case we can find just slack. Slack for the constraint 1 and 2, the result is equal to 0. Because it's binding constraint. They have this no slack and no surplus. In this case, if I ask you to find the range of optimality or change in the objective function coefficient here, or change the slope of isotropic line, you're gonna know that, okay, if I want to find range of optimality, the change of the coefficient in the objective function that make us to have the same optimal solution at point C. The slope of this isotropic line needs to lie between the slope of constraint 1 and 2, right? Needs to be 1 or 2 in order to have point C to be the optimal solution. And constraint 1, the slope is minus 4/3, I think. Yeah. Constraint 1, slope is minus 4/3. Constraint 2, the slope is minus 2. The slope of isotropic line is what? Minus 6/1 over 6/2, remember? So then, minus 6/1 over 6/2 need to lie between minus 2 and minus 4/3. And we split into two cases, remember? The case that coefficient in front of x1 to be the same as 7, and try to find the range of coefficient in front of x2. And another case, coefficient in front of x2 to be the same as 5, and we try to find the range for coefficient in front of x1. And this is the result. Okay? So this is the one that we just studied. Okay? Next, if we say that, okay, we just finished only this one. Now, we're going to study the safety analysis of changing the parameter in the constraint. As I mentioned to you that we allow just changing only the right-hand side, which is the amount of your resources. You share the money that you have as a budget. You share the amount of raw material. You share the amount of the labor hours, something like that. So what happened? So this one we did it already. For changing the right-hand side of the constraint, this one, we're gonna find two things. The first thing is about dual price, or sometimes we call shadow price, the same one. And the second one is the range of changing the right-hand side. Okay, change the right-hand side of the constraint. This is the second one that we're gonna analyze for safety analysis. And based on the change of the right-hand side of the constraint, we're gonna find two things: dual price or shadow price, and range of changing the right-hand side. Let's talk about the first one, the dual price. Dual price, what is this? This is a definition of dual price. And I can tell you more easier than this definition by using the word of mathematics. So actually dual price is about the value of z value, right? You apply the value of z value that change, right? The change from the original one based on you changing 1 unit of your right hand side of the constraint. You apply is about the z value that change from the original one based on you changing 1 unit of right hand side of the constraint. The apply can be positive and negative value, yes. And positive and negative, it doesn't mean just only the signal. Positive and negative values mean positive effect and negative effect. Positive result, negative result, something like that. Positive result is what? Positive result, if the problem is maximization, positive result you can refer to you have more profit. If you have the problem of minimization, positive result you can refer to you have the lower total cost. On the other hand, negative result is mean if you have the problem of maximization, you have lower profit. If you have the problem of minimization, you're getting the higher total cost. And the value of your price you can use to calculate, or you can be valid to use to calculate. Just only you change the right hand side of the constraint within the range that we're gonna find in the second part. Okay, based on this, okay, I will show you. It's not difficult, right? But it's it requires the understanding something about the concept, right? One thing that I need to tell you before I show you with the example. Firstly, I'm said that your price is about the z value or additive function value that change based on you change the right side of the constraint 1 unit, right? I didn't say that you change by increase 1 unit or decrease 1 unit. So it means you can increase the right hand side of the constraint 1 unit or decrease 1 unit. You can find your price. But for my suggestion in our class, I'm suggest you to using increase 1 unit to the right hand side of the constraint to be the way that we find the dual price. This is because in the printout of all the software program, including the Microsoft Excel, the dual price value that is shown in the printout is calculated based on you increasing 1 unit to the right hand side of the constraint. Okay. So in this case, I'm going to show you the example. Okay, look at this before we have a break. Okay, just the real quick one. This is the example of Fair Furniture Company. Optimal solution at point C, x130, x240. If I want to find the dual price of the first constraint, what are we going to do? Dual price for the first constraint. Okay, listen carefully and pay attention here. Original problem. This one is 240, right? Original problem, this one is 240. Based on original problem, okay, you have the first constraint, the black bar. This is the first constraint. This is the second constraint. And the orange shading is visible area. You assume some value to be the profit. You have isomorphic line to be the dashed line, the red one. Maximization, you project to this direction. Optimal solution occurs at this point, the black one. You solve for the solution x130, x240. Substitute x130, x240 to the objective function, we have total profit 410. This is original problem. Now we try to find the dual price for the first constraint. So then I'm changing the right side increased by 1 unit. So that's why I changed from 240 to be 241. And what next? I need to solve for the solution again. Firstly, I'm drawing the graph of the first constraint, which is the one that has 241 at the right hand side. So the graph going to change from the original one to be the blue or the purple one here. Because it changed to 241, so the graph going to shift to the right hand side. So right now, the first constraint, this is this graph, the blue one. This is the first constraint. And it's shading, right? Below the line. The second constraint to be the same. You have this one, and then you shading below the line. When you try to find the visible area, you have visible area, you have the same visible area and adding a little bit. Right? This is a visible area form this, right? The yellow, the orange one, and plus this area. You assume some value to be the profit here. you have this like the open line. You project to find the optimum solution, maximization go to this direction. It's going to contact at point C, the red point. This is optimal solution, the new one. At this point, you solve for the coordination. You find out that x1 29.5, x2 41. You substitute x1 29.5, x2 41 to the objective function. You have total profit 411.5. Now, I'm going to show you the value of U price. You can use the way of calculation based on you understand. But for me, I suggest you to using my method. It's easier and it will not confuse with the signal of the real time, positive or negative. Firstly, I don't care that the new Z value or the OC, which one is the better one. I just want to know about the gap or the difference between these two values. The OC is 410. The new one is 411.5. The difference between these two values is 1.5, right? So I'm writing down 1.5 first. And then I'm looking at the problem. The problem is maximize, minimize. It's maximization. Problem is maximization, you think about the total profit. So now you look at this. The old profit 410. The new profit 411.5. Profit increased, right?
Increase.
It's good or bad? Profit increased?
Good.
Good is positive result, so that's why new price is positive 1.5. We start the signal later on. Okay?
Okay.
So this is the way that we try to find the real time. And what is the meaning of this? It means that if you have more company labor out, more 1 hours more, you can expect to have total profit increasing by $1.5. So based on common sense, if you increase from 240 to be 242, what happens? You can expect to have more profit by $3. Right? If you have 243, you can expect to have more profit $4.5. 244, $6. Right? But it doesn't mean that, okay, if you want more profit, you're going to increase more and more and more. No way, because at some point you need to have like something that we call upper limit. That you cannot go further than that. In the real problem, in the real business problem, it means that if you increase the labor hour for the company work, it doesn't mean that you can have more profit, more profit, more profit. Because in some point, other resources may be run out of. It doesn't have anything after that. So that's why, for the second part, we try to find a way of changing this right hand side. In this case, maybe the upper limit that we cannot go further than that. And before we go further than that, we still use this group to calculate. But if you increasing more than the upper limit, you cannot using group 1.5 anymore. Lastly, before we have the break, if you try to find group type by decrease 1 unit, you can do it. For example, if I change to from 240 to be 239, what happens? When you join the graph going to shift to the side a little bit. It's cutting around here. You project this is the optimal solution. And doing the same method, you can find out that group height is going to be equal to minus 1.5. Okay. And for sure, they're going to have like some limit that we call lower limit, that you cannot go lower than the lower limit. Okay. That we can use the group height to calculate. Okay. So I'm going to stop here for the break. After you come back from the break, we're going to continue with the group price. And the last part with the range of changing the range size, and we will finish there. So now we have the please have the